In this video, we shall be finding the expectation and variance of the beta distribution of the second kind. For more on this topic, you need to subscribe to this channel. Solution. The expectation of y is equal to the integral from 0 to infinity y multiplied by f of y dy. So this is the expectation for the beta distribution of the second kind. The next thing to do is just to infuse the PDF into the expectation of x. So if we put the PDF into the expectation of x, we get the expectation of y to be equal to the integral from 0 ranging from 0 to infinity y multiplied by 1 all over b alpha beta multiplied by y all over, here is alpha minus 1, and here is 1 plus y alpha plus beta dy. So this is what we get. The next thing to do, we can bring this out here. So it then means we go over to this side. So that means our expectation of y will be equal to, we bring this out, 1 all over the beta distribution alpha beta integral from 0 to infinity. Of course, we now have this as y into this, y will multiply this to give us y into alpha plus 1 minus 1 all over 1 plus, okay, we can write it as y plus 1 raised to the power of alpha, we can say plus 1 minus, plus 1 plus beta minus 1, the y. Still the same thing. Alpha plus 1 plus beta minus 1 is the same thing as alpha plus beta. So the next thing to do, we know that the whole of this function means something. So our expected value of y will be equal to 1 all over the beta distribution alpha multiplied by alpha beta multiplied by the whole of this function. The whole of this function will give us our beta distribution to be alpha plus 1 and beta minus 1. So it then means that our expected value of y is equal to our beta distribution alpha plus 1 beta minus 1 all over alpha beta. So this is what we get. The next thing to do is for we to write what this thing means. That means we use the gamma function to write this. If we are using the gamma function to write this, we have the whole of this function, will give us alpha plus 1 and beta minus 1 all over alpha plus beta all over. We now write the whole of this. We use the gamma function to write this beta distribution here, and it will give us alpha multiplied by beta all over alpha plus beta. So the next thing to do is just to rewrite this, and we'll come over to this side to rewrite it. So the next thing to do is to rewrite this. So we'll come over here. I'll have to clean this. So rewriting this, we get our expectation of y to be equal to alpha plus 1 into beta minus 1 all over alpha plus beta multiplied by, this will go over to this side to give us alpha plus beta. That means this will go over here and we have all over alpha beta. That is it. And we should note that from the gamma property that this function, that is, note that this function alpha plus 1 is equal to alpha into alpha. And we should also note that from the gamma property, beta minus 1 is equal to beta all over beta minus 1. So infusing the whole of this into here, we get our expected value of y to be equal to alpha into alpha multiplied by, if we put this here, this will also come down. So we have beta all over, let's write it out, beta minus 1 all over alpha plus beta multiplied by alpha plus beta all over alpha beta. So of course, this can cancel this can also cancel this. So let us rewrite this word before we cancel. Let us rewrite it well. It will take us to this other side. It will take us to this side. So if we rewrite this well, we'll have the expected value of y to be equal to alpha into alpha multiplied by beta all over beta minus 1 into alpha plus beta multiplied by alpha plus beta all over alpha beta. So this is what we'll have. Of course, this will cancel this. This will also cancel this. While this function will cancel this function. So it then means that our expectation of y is equal to alpha, which is remaining here, all over beta minus 1. So this is what we get for the expectation of y. We are asked to find the expectation and the variance. But before we find the variance, we also need to look for the expected value of y squared. The expected value of y squared. So we come over here. The expected value of y squared is equal to the integral from 0 to infinity. We have y squared f of y dy. So this is what we get. If we want to look for y squared, this is what we get. The next thing to do is to infuse the beta distribution PDF into this. So if we infuse it, we get the integral from 0 to infinity. We have y squared. If we remember, we have our distribution as 1 all over beta alpha beta into y alpha minus 1 all over 1 plus y raised to the power of alpha plus beta, then dy. So this is what we get. So the next thing to do is to bring this out. For we to bring it out, this is our expected value of y squared. So the expected value of y squared will be equal to, we bring this out to give us 1 all over the beta alpha beta multiplied by the integral of 0 to infinity. This y will go back to this, we'll have it as y to be y plus, y alpha plus 2 minus 1 all over, we can say y plus 1 into alpha, because of its y squared, we now put into alpha plus 2 plus beta minus 2 dy. It's still the same thing. Of course, the whole of this function means something. So we now multiply what we have as the whole of this function with our beta distribution here. So we come over again to this side. We come over to this side. So the whole of this function will now multiply it with this. So we have our expected value of y squared to be equal to 1 all over our beta distribution alpha beta multiplied by the whole of that function. The whole of that function will give us beta into alpha plus 2 and beta minus 2 bracket close, which is the same thing as beta into alpha plus 2 beta minus 2 all over. We also bring this one down to give us beta distribution into alpha beta. So the next thing to do is to write what this function is and what this function is. But we are using the gamma property to write it out. So it then means that the whole of this function is equal to, using the gamma function to write it, you have gamma alpha plus 2 into gamma beta minus 2 all over beta. Then we'll write this function. The whole of this function means alpha beta all over alpha plus beta. So the next thing to do is to rearrange that. is to rearrange all of this. It will now take us to the other side of the board. To take us to the other side of the board, we also should not forget that the expected value of y is alpha all over beta minus 1, because we'll come back to this when looking for the variance. So I will be explaining the whole of this part. So rearranging this, we have our expected value of y squared to be equal to alpha plus 2 into gamma function of beta minus 2 all over beta. But in the beta distribution of the second kind, we add the degree of freedom adjustment. The degree of freedom adjustment, we add it to be the gamma property alpha plus beta minus 2 multiplied by, we put this will come over to give us alpha plus beta all over alpha beta. So this is what we get. Of course, the whole of this means something. The whole of this means something. And we should note that from our gamma property, alpha plus 2 is equal to alpha plus 1 alpha. So we put the whole of this into this to give us, to give our expected value of y squared to be equal to alpha plus 1 multiplied by alpha, okay, into alpha. So our alpha plus 2 will give us the whole of this, which is alpha multiplied by our gamma function beta minus 2 all over beta multiplied by our degree of freedom adjustment, which is always added for the beta distribution of second kind. Then we have alpha plus beta all over alpha beta. So of course this will cancel this to give us alpha plus 1 alpha multiplied by beta minus 2 all over, we can still multiply this, which is alpha plus beta. We bring this here, this multiplied by this will give us beta raised to the power of 2, that is beta squared, multiplied by this function alpha plus beta minus 2. Also, we can also expand this. We can use our gamma property to write this, which implies that we have alpha plus 1 alpha multiplied by beta minus 2 dot alpha plus beta all over beta squared. We can expand this and it will give us alpha plus beta and alpha plus beta plus 1 into alpha plus beta. So of course this will also cancel this. Then if we have this and this, using our gamma property, the whole of this will give us what to cancel with this, and we'll get our final answer for the expected value of y squared to be, we come over to this side, we come over to this side, we come over to this side, it then means that our expected value of y squared will be equal to, we'll bring this out, alpha plus 1 into alpha all over. If we cancel this, the whole of this, if we rewrite it with our gamma property, we'll get beta minus 1 into beta minus 2. So this becomes our expected value of y squared. Then how do we calculate for the variance? Now we go over to the variance. Of course, we know that the variance of y is equal to the expected value of y squared minus the expected value of y all squared. So we have this as our expected value of y squared, which is alpha plus 1 into alpha all over beta minus 1, beta minus 2, minus, we remember that we got alpha all over beta minus 1 for our expected value of y. I said we will refer back to this. We shouldn't forget it. Because of this square sign, we have square here. So our variance of y is equal to this. We will also move over to this other side so that we can simplify the whole of this function. So simplifying this function here, we move over to this side. We move over to this side. If we move over here, we have our variance of y to be equal to alpha plus 1 alpha all over beta minus 1 beta minus 2 minus alpha squared all over beta minus 1 squared. So simplifying this, it means we'll find the LCM of this and this. So finding the LCM of this and this, we'll come over to this side. We'll say beta minus 1, beta minus 2, and beta minus 1 squared. If we are looking for the LCM, we use beta minus 1, we'll get beta minus 2 and beta minus 1. We say beta minus 1 again, we get beta minus 2 and 1, because beta minus 1 into beta minus 1 will give us 1. The next thing to write is beta minus 2. So we have 1, 1. So our LCM for this function will give us, beta minus 1 squared and beta minus 2. If we multiply what we get here. So this is our LCM. We now use the LCM to simplify the whole of this. It then means that we have beta minus 1 squared and beta minus 2. So this goes into this. If this goes into this will cancel this. This will also go here. So we just have beta minus 1. So we multiply beta minus 1 with this to give us beta minus 1 multiplied by this. We can multiply this as well. Alpha squared plus alpha minus this into this. This can cancel this. So we have alpha squared multiplied by beta minus 2. So this is what we get, which is our variance of y. So that is what we get. So the next thing to do is to open the whole of these brackets. If we open these brackets, we get this multiplied by this will give us alpha squared beta. This multiplied by this will give us minus alpha squared. This multiplied by this will give us plus alpha beta. This multiplied by negative 1 will give us negative alpha minus alpha squared multiplied by beta will give us alpha squared beta. Alpha squared multiplied by 2 will give us positive, because of negative will give us positive 2 alpha squared all over beta minus 1 squared and beta minus 2. Of course, this will cancel this, and we have negative alpha squared here and 2 alpha squared. It then means minus 1 plus 2 will give us 1. So we can write this as alpha squared plus alpha beta minus alpha all over what we have here, beta minus 1 squared and beta minus 2, which is our variance of y. We can still rewrite this well, although this is our variance of y, but we can open the brackets here. For me to open the brackets here, I would not like to tamper with this part. So it will give us, if we like to write, it will give us alpha into alpha plus beta minus 1 all over beta minus 1 squared beta minus 2. So this becomes our answer for the variance of y. So this is how we can compute the expectation and the variance for the beta distribution of the second time. If we follow this process, we can obtain the expected value and the variance for the beta distribution of the second time. For more on this topic and many other, you need to subscribe to this channel.